Good afternoon, everybody. It's great to see you all here. It's a great pleasure for me to welcome our speaker today, Anne Willier. She is world famous for her pioneering work on attosecond physics, which means a lot to some of us in the department who also work on attosecond physics. She received the Nobel Prize in Physics in 2023, along with Ferenc Krauss and Pier Agostini, for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. And that's very close, I think, to the title of her talk today. Anne, I think, was born in Paris and then studied maths and theoretical physics in Paris before moving on to an experimental PhD at the Pierre and Marie Curie University, also in Paris. But I believe most of your experimental work was done in the CEA labs in Saclay, where she carried out this groundbreaking research that discovered high-order harmonic generation driven by intense infrared lasers, which is the doorway to attosecond physics. And her huge contribution was the development of the insights that led from that discovery to the widespread development of attosecond science that we now have today. In 1994, Anne moved to Lund, where she leads a renowned experimental group in attosecond science and is still very active to this day. I should say she is also married to Klaus Goran Wallström, who was a former postdoc working in our department in the Extreme Light Consortium, and I guess was one of the reasons you went to Lund. She has, of course, received many awards and recognitions for her work, including the 2022 Wolf Prize, awarded to her and Ferenc Krauss and Paul Corkum. So Anne has visited this department on a number of occasions over the years, and we're delighted to welcome her back for this talk. So thank you, Anne.
Thank you very much. I'm really very happy to be here. So this talk is a little bit of a mixture between what I'm calling a Nobel lecture and a little bit more specialized towards the end. So, and this is the outline of this talk. First, I'm going to talk about high-order harmonic generation, a little bit where did it start, and then attosecond light pulse, and then what we do with these pulses. So let me start with the first laser, which was invented by Theodor Meinmann in 1960. And it was a ruby laser. None of what we have been doing would have existed without the laser. Laser invention opened new research in physics. One of them is nonlinear optics. Here you have an experimental setup for the second harmonic generation. In a piece of quartz, you have laser, focusing lens, piece of quartz, prism to analyze the radiation, and then you have a detector. And already in 1961, they could observe the generation of the second harmonic through this process. Another field that was opened thanks to the invention of the laser is atoms in strong laser fields, multiphoton processes that were discovered theoretically or predicted theoretically by Maria Goppert-Mayer in 1931. You have here two-photon excitation process. You can also multiphoton ionize atoms. This was pioneered by Russian scientists in the 60s. 1979, Pier Agostini and his group in Saclay, France, observed the phenomenon of above-threshold ionization, where atoms can absorb more photons than what is strictly needed for the ionization. And you can detect these processes by looking at the electrons that are being emitted. My thesis work was in the beginning of the 80s, and it was to study multiple ionization processes by multi-photon absorption. You have here, for example, a double ionization of xenon atoms. At that time, it was clear that atoms could really absorb many photons, and probably we would create excited atoms or excited ions. So we thought that maybe we could learn more about these excited systems by looking at the fluorescence emitted by this species. So at that time, I was a young researcher at the CEA, Commissariat à l'énergie atomique in France. So we set up an experiment where we look at fluorescence emitted by atoms exposed to strong laser fields. And here's a picture of the laser that we used at that time. Shows that things have changed. This was a neodymium YAG laser, 1 micron wavelengths, 40 picosecond, 10 hertz repetition rate. We did not see fluorescence. What we saw instead was high-order harmonic generation. And here you have one of the first spectra obtained in argon gas and showing 13s, 15, up to 31 harmonics. You can notice that it's only odd orders, and this is because of the symmetry of the interaction, symmetry relative to the origin. If you plot the distribution of these harmonics as a function of order, you find this kind of characteristic behavior with the first decrease, which was expected, plateau behavior, and then a cutoff. And I would like to say that the discovery was really this plateau behavior, because at the time we were thinking very much in terms of perturbation theory. And if you so if you expand here the polarization induced in the medium by the laser, for such an expansion to be valid, you need the first order to be much stronger than the third, much stronger than the fifth, etc. And this was obviously not the case, because you have this plateau behavior. So strongly, highly nonlinear, non-perturbative phenomenon. If you look where we are in the electromagnetic spectrum, we are starting from the infrared, but then you multiply by a rather high integer, you end up in the extreme ultraviolet region of the spectrum. And if some of you here are really not at all in this field, I like always to make a little analogy with music. People usually have heard about harmonics in music, and this is a spectrum that you can get if you play violin. It's never a pure tone that you play. You get a tone plus many harmonics, and you can see that these two spectra are kind of similar. In both cases, you have a strong interaction here between atoms and a strong laser field, and here between the string of the violin and the bow. Of course, these are acoustic waves. Here we have optical waves with completely different type of waves, but similar phenomena. What I found very nice as a young researcher is the fact that this phenomenon is really in between two different fields. One is atomic physics, quantum mechanics. An atom is exposed to a strong laser field and generate all of these high harmonics. This is described by the Schrödinger equation that you have here with an atomic potential and then the laser-atom interaction, which you can usually describe with the dipole approximation, as shown here, and with the classical field. But the difficulty is that this is strong, comparable to the atomic potential. But you also need to consider the nonlinear optics part of the problem. You need to take into account the response of the medium to the interaction and how the emission from the different atoms builds up. This is described by a Maxwell equation or by a wave equation, as you see here. This describes the generation of a certain field. due to a polarization in the medium. This is also called phase matching. In order to get harmonics, you need a certain phase matching condition to be realized. The first attempts to understand this phenomena was actually to solve numerically these two equations. This was done at the end of the 80s, particularly by the work of Ken Kullander and co-workers. Now let's move on a little bit in this little bit historical perspective. We're coming to the end of the 80s, beginning of 90s. Huge progress in laser technology, with 3 discoveries at the same time, almost. The discovery of the chirp pulse amplification technique that would lead to a Nobel Prize to Gérard Mourou and Donna Strickland in 2018. A new laser material, titanium sapphire, and also a new technique to generate short femtosecond pulses called Kerlens mode locking. And in Lund, Sune Svanberg, Klaus-Göran Wahlström, decided to start really a new facility to really get going with this new technology, with the first terawatt titanium sapphire in Europe at the time. And I think this is in this time that Klaus-Göran was sent to Imperial College to learn about high-order harmonic generation, 89, 90. In parallel to that, in Saclay, we built new instrumentation to really study this phenomena. And you have a photograph of this instrument with myself a long time ago. My first 2 students, Philippe Balcou and Pascal Salière. And Pascal Salière is still in this field. What do you have in this instrument? Well, you have basically the same thing I showed you at the beginning. We have a lens that you see here. The laser is behind the wall. You have a gas jet. You can see the tube here. You have optics, which are in this chamber here, and then a photon detector, which in this case an electron multiplier here. In Saclay, and I guess at the Imperial College, if I understand right, approximately the same time, they had a very big neodymium glass lasers, and they implement the new chirp pulse amplification technique. And so this is the laser we could use, 1 picosecond pulse duration, horrible repetition rate, 1 shot per minute. Can you imagine? And this is a time where in Lund they called me and say, oh, we have a brand new laser. Would you like to do experiment with this laser? And oh, please, could you take your new instrument with you? And this is what we did. We sent this instrument in a truck, and we drove to Lund, not with the truck. And we did experiment with this fantastic laser, titanium sapphire, 200 femtosecond, 10 hertz repetition rate. So it was a huge difference. And this is one of the first results obtained in helium with this laser showing beautiful plateau. You should imagine it really a very, very long plateau, really constant intensity. And then this cutoff. I would like to say that we were at that time. Now, Attosecond research there are several places in London, for example, 3 places, many places in England, in the UK, many places everywhere. But at that time, we were only a few laboratories doing this research, and one of them was Imperial College. I was before coming here, I actually looked at all the publication, we were competing a little bit between Saclay and Imperial College. It was led by Henry Hutchinson at the time. This is, for example, a beautiful spectrum obtained, I believe, using this neodymium glass laser. And so I guess with a very bad repetition rate. I'm looking at John Morangas. John Tish, you were also part of that, I guess? Wasn't too bad. And this is, I think, the first angular distribution that were recorded in about high-order harmonic generation. And another result, the first time harmonic generation in other gas than rare gases were obtained here in butane and butadiene. So it was also, I believe, really I think a very important result because it led to all the harmonic spectroscopy field afterwards. Okay. This was the first part about high-order harmonic generation. What about attosecond pulses? So I think the idea about attosecond pulses arose very early after the first experiment in 1987, because it's kind of natural idea when you work with mode-locked laser. And it was in particular pointed out in these two publications. And the idea is the following. This represents 3 harmonics. If these harmonics are phase-locked, which means that the maxima of these 3 harmonics happen to be at the same time, and because of the periodicity of the process, every half laser period, here you have the minima at the same time, and then the maxima again, etc. So if this is true, and you sum these 3 harmonics, you get a train of very short light pulses. This is the intensity of this train of attosecond pulses. Here is just for 3 harmonics. If you have 10 harmonics, you can even get shorter pulses. And the reason, so the half laser period for titanium sapphire is 1.3 femtosecond. So you see that here we are clearly in this attosecond time scale. The reason why it's like that, it's because we have a high frequency. We are in the extreme ultraviolet region of the spectrum. So in order to have short light pulses, you need to have a short optical period, and you need to have high frequency. We have large bandwidths, all of this plateau, so a very large bandwidth. So you see that these high harmonics fulfill these criteria. So the question was, are the harmonic phase-locked? And actually it's going to take us as a community 14 years to really be able to answer this question. At the beginning, we were very skeptical. It really took us many years to understand enough to start believe that yes, maybe, and then finally the measurement of attosecond pulses was very important. Huge progress in understanding with the 3-step model, which was proposed by Kullander and co-workers and Paul Corkum, and it was formulated with the strong field approximations, quantum formulation of this by Maciek Levenstein and co-workers. And here's the cartoon showing this 3-step model, a very nice intuitive picture of the interaction between an atom and a strong laser field. So what you see here is the atomic potential, which is strongly deformed by the laser, so that there is a certain probability for an electron in the ground state to tunnel through the barrier, and the electron is driven away. It's coming back when the laser change of sign, and then there is a certain probability for recombination back to the ground state and at the same time emission of short light pulse. This you can see if you look at the electron trajectories. You find that depending on the time of ionization of the electron, you have different electron trajectories coming back at slightly different times, but within 100 attoseconds and with a certain bandwidth of tenths of electron volts. So you have this emission of, you have an attosecond electron wave packet that leads to the emission of an attosecond light pulse. So now I have a light version of this, a little bit for the students here. The older people can do something else. I don't know if you have seen this before. It's kind of analogy. The name is The Adventure of an Electron in a Laser Field. Was actually an idea by Philippe Balcou when he defended his thesis. So you have an electron. This is in Swedish. This is why it's like this. In a laser field, you can represent it like this. This is an electron in a prison. And it's good that it is in a prison, otherwise we would not exist. It's a strong force. And this is a roller coaster. What does the electron do? You have to speak loudly. Yeah, but he needs to go to the roller coaster. How does he go to the roller coaster? It tunnels out. I get the right answer directly. Thank you. Yes. Yeah. This is part 1. Part 2. Everything is great. This means acceleration in the laser field. So the electron is going down and up. It's very happy. This story is finishing very bad. I guess you can guess. Yes. Yes. So the roller coaster finds the open prison on its way. So the electron is just falling and liberating its energy by screaming out. This is our attosecond light pulse. Have you seen that before? No? Okay. All right. That's it. Yes. So to have the full picture and to connect to the generation of high-order harmonics, you need to consider several of these trajectories, adventure of the electrons, every half laser cycle on both sides of the atom, and the emission of attosecond pulse train every half laser period with actually a change of sign every consecutive attosecond pulse. And now if you go into the frequency domain, you recover your spectrum of high-order harmonics, odd high-order harmonics. What is the reason for the plateau? It's really the short time emission is in the frequency domain, this plateau behavior. So I've talked a lot about the response of a single atom to the radiation field. As I say in the beginning, to have the full picture, you also need to consider phase matching. So let me first give you a very simple picture, and then I will be a little bit more specialized. I start with a simple picture. Roughly what you want to have is that the phase velocity of the fundamental field in the medium equal to the phase velocity of the field that is generated in the medium. In other words, that the two refractive index should be equal. Let's look at the refractive indices as a function of frequency. This is from the book of David Atwood. For the fundamental frequency, the refractive index is larger than 1. However, for the high-order harmonics, we are in this ultraviolet, extreme ultraviolet region. The refractive index is less than 1. So this is not possible. Fortunately, we do have some free electrons in the medium because we have partial ionization of the medium. Some of the electrons, they do not come back. They are just being emitted, so contribute to partial ionization of the medium. And this leads to a reduction of the refractive index at the fundamental frequency, so that it's possible for certain degree of ionization, we see typically a few percent, that the two refractive index becomes equal. So that means that this phenomena is possible during a certain intensity window. The intensity needs to be strong enough to have the generation of these high-order harmonics, but the intensity cannot be too high. Otherwise, you ruin phase matching. Now, in reality, it's a little bit more complicated than this. There are also the effect of focusing of the radiation, also the effect of the electron trajectories accumulating a phase. Recently, we actually looked at the conversion efficiency of the 23rd harmonic in argon as a function of pressure and medium length. And these are in a little bit strange unit to take into account the geometrical scaling of high-order harmonic generation. So this is as a function of the Rayleigh length, and this is here the product of the pressure times the Rayleigh length. And we found that actually you obtain the best conversion efficiency, typically just below 10 to minus 5, not in one point. So there is not a best pressure and length, but actually it's a hyperbolic behavior, which was, for me, a very nice result, because it explained why everywhere in the world people generate harmonics different ways. They use gas jet, high-pressure gas jet, they use long cell, they use semi-infinite medium, they use capillaries. It seems that it works anyhow. So I think this behavior that we found really shows that, yes, you can have achieve phase matching in this region, high pressure, small medium, or here, low pressure and long cell lengths. And you can even identify different regime of phase matching. If you are here along this vertical branch, that means that the effect contributing to phase matching is mostly the atomic dispersion and free electron, exactly as I explained before. So this is really a regime of transient phase matching, more or less pressure independent. In this, along this horizontal branch of the hyperbole, then what is important now is the effect of the phase variation across the focus, the GUI phase. So in this case, phase matching is only weakly dependent on the medium length, and in general, the radiation is more collimated. This is a part where we're still learning things after more than 30 years after discovery of high-order harmonics. We are still learning how to control it better, how to optimize it, and even how to understand really basic things like phase matching. Now I'm coming to the measurement of attosecond pulses. As I said, this was really very important for the field to really show that, yes, we have attosecond pulse. And let me briefly present to you the two measurements performed first by Pierre Agostini, attosecond pulse in a train of pulses, and then by Ferencváros. So here is the idea used by Pier Agostini based on a theoretical proposal by the group of Alfred Maquet in Paris. So the technique is based on two-photon ionization, where you use one harmonic and a laser photon to create a sideband. This sideband can also be reached by absorption of the next harmonic and emission of one photon. This technique is called rabbit, reconstruction of Attosecond beating by interference of two-photon transition. So here you see that this sideband can be reached by two quantum paths. You need to add the amplitude of the two quantum paths. And when you add the amplitude, what you get will depend on the relative phases of these two amplitudes. So let's look at the phases. First, you have the phase of harmonic Q here, plus a contribution due to the ionization. For the moment, let's neglect it. I come back to that a little bit later on. We have a phase due to the next harmonic, and then we have a contribution of the laser. Laser is delayed relative to the harmonics by a delay tau. So if you just sum the phases, or take the difference between the phases, you obtain a signal which is in the cosine term, you have this phase difference equal to 2 omega tau plus the difference of the phases of harmonics, consecutive harmonics. And this is what I really want to measure, because what I want to do is to check the phase locking condition. Is the phase of harmonic Q equal to phase of harmonic Q plus 2, or how close are they? So this is the measurement that was performed by Pier Agostini. I'm not showing you detail. They did this measurement in argon, combined with measurement of the intensity of the harmonic, and from that they could reconstruct the pulse train. And this is the measurement showing a pulse train with pulses with duration 250 attosecond. More progress in laser technology. This field has been really driven by laser technology and is still being driven by laser technology. At the end of the 90s, you have really progressed toward few cycle pulses with post-compression techniques in hollow fibers. And this morning I have seen many hollow fibers, so this is still used quite a lot. And you can, in hollow fibers, you broaden the pulse, which then you compress by chirp mirrors. This is a picture of a setup in, I believe, in Milan. And also the realization that carrier envelope phase of these pulses matters, and carrier envelope phase is the difference here between the electric field maximum and the maximum of the envelope. And I think Imperial College has been really leading this part very much. I remember this half-cycle cutoff that you were producing. And anyway, using this very short light pulse, Feldenkrais and his group, at the time in Vienna, then moved to Garching, they could not only measure attosecond pulses, but also generate attosecond pulse simply by using very short laser pulses to begin with. And using the streaking camera technique, you have here one very famous streaking trace showing a pulse with duration 250 attosecond. Here, the idea is simply that you you ionize an atom by absorption of XUV light, this very short attosecond pulse, in presence of a laser field so that the momentum of the electron is affected by the laser field, can increase or decrease it depending on the delay between the XUV radiation and the laser cycle, and leading to a decrease or increase of the electron kinetic energy. And from that, you can retrieve the pulse duration. I'm now coming to the last part of this talk, which is a little more what we are doing now. So it will be a little bit more specialized. So what do we do and how do we use these pulses to study electron dynamics? And I'm going to concentrate on maybe the simplest process, which is photoionization of atoms, which was, this is the photoelectric effect discovered by Hertz in 1887 and explained by Albert Einstein in 1905. So first of all, the experimental method, and we're going to use the same rabbit technique, which was pioneered by Pier Agostini, this time to extract information about the photoionization process. So this is the experimental setup that we use in Lund. It's based on Attosecond interferometry, which requires an optical interferometer, shown here. We split the laser into two. In one arm, you generate high-order harmonics or your Attosecond pulse train. We remove the fundamental field here with a metallic filter. And then in the other arm, we have a fraction of the laser, which is delayed relative to the other arm. And this needs to be very precise. We use active stabilization to have a very stable interferometer. And this is our tool. It's not only the Attosecond pulses, it's really Attosecond pulse plus this probe field at a variable time delay. Then we send this two field into a vacuum chamber where we have the gas that we want to study, and we simply measure the electrons that are being emitted and measure their energy, for example, using magnetic bottle spectrometer. This is a typical trace that we obtain. It's called rabbit trace, rabbit spectrogram. So what is shown here is the electron spectrum as a function of the delay. So what you see are lines. So the main lines or main bands are due to absorption of the harmonics. And in between you have the side bands due to this extra absorption or emission of one laser photon. And if you look, you see that these traces nicely oscillate, and the period of the oscillation is half the laser period. Using titanium sapphire is 1.3 femtosecond. And this is where the information is contained. It's the phase of the oscillation of the sideband. So this is what we measure, is what is the delay and how this delay is changing as a function of frequency. And this has been used typically in two types of experiments. I'm going to show you actually example in both cases. One is in non-resonant ionization to ionize a gas with attosecond pulse over a broad spectral range. So create a broadband attosecond wave packet, which is shown in blue. And so what we try to do is not only to measure the intensity, the probability of ionization, but to measure the phase of this attosecond electron wave packet. And how do we have access to this phase? By using this interferometric rabbit technique. These red photons allows us to probe the phase of this attosecond electron wave packet. The other way has been in some cases, we are looking at an attosecond wave packet with narrower bandwidths, for example, due to resonant ionization, for example, close to a discrete state, like here. And we want to, again, to read the phase of this wave packet using these interferometric techniques. So here it's really attosecond dynamic, broadband, while here is more femtosecond dynamic, more narrow band. You need a good spectral resolution here. But same type of interferometric technique to read phase information. So let me show you an example of this type of measurement, which has been done by, actually pioneered by the group in Garching, using not really rabbit, but streaking type of measurement, but which we have used in other group in the world quite a lot. And so let me show you one example. And first of all, let me comment a little bit on the physical signification of this delay that we measure. Actually, there are three contributions to this delay. One is, of course, the group delay of the attosecond light pulse, which Pierre Agostini and co-workers measured in the first rabbit technique. So and this is the most important contribution. And then you have a group delay of the photoelectron, which is, I think, the most interesting quantity on the physics point of view, which is really coupled to the ionization process. And then you have a small correction due to the fact that you need to have this absorption and emission of a photon. It's called continuum delay. This is mainly at threshold, so I'm going to ignore that in the example I'm going to show to you. So let me comment a little more on this delay here. It's called TW, W like Wigner, because it was actually introduced by Eugen Wigner in 1955. And this group delay, I think if you want to think of it physically, is the delay which the attosecond electron wave packet acquires when it propagates out of the atomic potential. And it's related to the scattering phase, which is well-known quantity in collision theory. It's actually the half the derivative of the scattering phase, which is the difference between the phase of the electron, asymptotic phase of the electron going outgoing, and the phase of a free electron. So now let me move to the example I want to show you, and this is about 3s ionization of argon atom, which is a problem we have been studied, I don't know, like 14 years. So one of my messages is that research takes time, and it takes time to really understand, to do good experiments and to do good theory as well. So I'm starting by showing you the cross-section of ionization in the 3s shell of argon as a function of energy in the region which is called the Cooper minimum. So it's not really a normal Cooper minimum, which corresponds to a transition matrix element going to zero. It's a kind of image of a Cooper minimum due to 3s3p correlation effect, interchannel coupling. This actually was predicted by Amusia in 1972. So you have this minimum, and here you have experiment and theory. This is a well-understood problem in 1972, using in particular a theory called random phase approximation with exchange. Nice, we understand why there is this minimum is due to coupling between the 3s ionization, 3p ionization, which is very strong. Now we look at this ionization delay. And this is what I would like to measure. Or this is what I would like to measure. First of all, I remove the tau cc, which is small in this region. So let's me forget it. But you still have these two contributions here. So how can I distinguish? Well, one thing you can do is you can ionize argon both in the 3s and in the 3p shell at the same time. And then you take the difference. And in both cases, this is the same. So if you take the difference, this is cancelled. So you just get the difference between these 2 times delay. And these are recent experiments performed by a group of Chinese researchers. So you have this experiment, but before we also did experiment in Lund and also in Saclay. So the experiments show this difference in time delays going down. Forget the red curve for a moment. The random phase approximation with exchange, which explains so well the cross-section, gives this result here. And during 10 years, who is right? The experiment or the theory? It was really back and forth between theorists and experiments on this problem. First of all, what is the contribution of 3s ionization and 3p ionization? If you do a little bit of atomic physics, you realize that what you see here and this bump here is due to 3p ionization. Here, no problem. Very good agreement between theory and experiment. In this case, error bars are big, but they are experiments in particular by the Saclay group where it's very nice agreement in this region. But here, the region of 3s ionization, huge discrepancy between the blue curve and the experimental data. So discrepancy of a few hundred attosecond. Very different physical picture. In one case, the blue curve, this means that the electron is trapped in the potential. It is delayed. While in this case, going down, the electron is pushed away. It's ionized very rapidly. So you see very different physical picture. Same, which is not shown at all in the cross-section. So recently, Eva Lindroth did some further calculation and included more correlation effect with shake-up channels and shake-up correlation and obtain this red curve. So I think now we understand what is happening. And basically what I want to say here is that this phase information that we get is really new and is really brings something more to the physics than just cross-section measurements. And in this case, tells us that these channels are important. Now, I would like briefly to show you another example where this kind we create a little bit narrower electron wave packet. This is ionization of helium, close to the 2s2p state. And this is a beautiful example of quantum interference effect between, you have interference between direct ionization and photoexcitation followed by auto-ionization, correlation effect, again. And we look at this, we look at the phase of this wave packet by making a copy of the wave packet on this sideband state and measuring the phase using the same technique. And this is the result. This is obtained with the narrow bandwidth probe field. And you see here that we get a very nice interference pattern for the amplitude and a phase jump of pi for the phase. And what is very nice, now we have amplitude and phase information. We can go in the time domain by Fourier transform, or you can even do a time frequency representation of photoionization. And this is what is shown here. This is a Wigner distribution. What you see here, so this is time and energy, and this is again the Wigner distribution. And what is shown is that first you have mainly photoionization, which is short in time and broad in frequency. Then you have strong interference effect in this region. And finally, at later time, you have mostly photoexcitation followed by autoionization. So when we did that, we asked ourselves, can we always do that? We create photoelectron, can we always think of it as a kind of like an optical wave with a phase and amplitude? Well, you cannot always do that. Very often, especially if you go to more complex systems, molecules, etc., you have many processes and you do not get a coherent wave. So we ask ourselves, can we do better? Can we measure not only phase and amplitude, but really the quantum state of the photoelectron that is being emitted? So here is a new technique where we used to look at this photoelectron, a probe field now made of two frequencies, so a bichromatic probe. So a pump is a harmonic, and the probe is a bichromatic probe field, which we sculpt in the laser spectrum using a forest shaper that you see here. You have two grating, two focusing mirror, and here in the focal plane we have slits in order to pick a few frequency components. So how does this technique work? Again, we copy this wave packet, we create a sideband, but now by absorption of these two frequencies. Just to make you understand this a little bit better, I draw here two XUV photons and a few states. So we look at a final state here. You can see that we have again an interference pattern. You go to the final state by two different paths. And now if I look at the signal, this sideband signal, as a function of delay between the bichromatic probe and the pump, I'm going to see beating interferences. And this beating now depends not on 2 omega, but on delta omega, which is the frequency difference between these two frequencies. And now, what does this signal mean? Well, you see that the contrast of the interferences is going to depend on whether there is a well-defined phase relationship between the two states of the photoelectron wave packet. In other words, this contrast here depends on the density matrix of the photoelectron at these two energies, epsilon 1, epsilon 2. And the phase gives us the phase of the density matrix. So what we do by doing this measurement and then varying the frequency difference between these two frequency components is really a quantum state tomography of the attosecond wave packet. We call this technique, it's not my invention, because I think it's a very bad acronym. First of all, you need to write it in Swedish, and this is the Swedish translation of this, and so the name of the technique is called Kraken. So, yes. So these are Kraken measurements. So it's very similar to rabbits. It's really an oscillation that we look at. And we look not only at the phase of the oscillation, but at the amplitude of the oscillation. And this is what you see here for different pairs of these two frequencies. And from these oscillations, you can deduce the off-diagonal matrices of the density matrix that you see here. This is for helium. So this density matrix is energy, energy. And yeah, we can measure these different off-diagonal elements. This is a sparse matrix. Then you can use some algorithm to retrieve the matrix, and this is a result obtained in helium. It's very nice, it's round, it's a pure state. No surprise, it works. And now you do the same measurement in argon, and this is what you get. Oh, first of all, I can say that you can calculate the purity, and it's very close to 1. So you do the same measurement in argon, and this is what you get. It's not round anymore, it's elongated, which means that there is obviously loss of coherence here on the side. So it's really the density matrix of a mixed state. And what is the reason for that? The reason is it's called spin-orbit interaction. And in argon, you have two different finer states. You have two different states of the ion, which are produced, P1/2 and P3/2. So the electron can be created with this energy or this energy. In other words, when you ionize argon, you create an entangled state, depending on whether the ion is left in the 1/2 state or in the 3/2 state. We are not measuring the complete system, ion plus electron. We are only looking at the electron. So what we do is really a trace of the state corresponding to, or the density matrix corresponding to the complete system. And because of this entanglement, we have a mixed state. The purity is measured to be 0.65 if if there was no overlap between the two electron states, then it would be 0.55. So there is some overlap here which reduce the degree of entanglement. So I think I'm coming to the end of this talk. What is the next chapter in Attosecond science? I think this field is not finished because there has been a Nobel Prize. I think it's just the contrary. Now it really opens up in very many directions. I think one of the challenge of the field is really to use this very short light pulse to study complex systems, molecules, or condensed matter. There are many directions as listed here. And of course, what is very exciting is that now you have different sources for attosecond pulse, not only with high-order harmonic generation in gases, but also in solids, and also especially you have attosecond pulses using free electron laser, leading to attosecond pulse with different characteristics, more in the X-ray range and with higher energy per pulse. So I'm now almost finished. I want to just tell you that if you are lucky someday and you are happen to be at the right time, the right place, long time ago, you might end up here. And this is a picture of the ceremony in Stockholm with the royal family. I think Yom was somewhere in the audience here, yes. And yeah, these are the Nobel Prize laureates. You have Pierre Agostini here, Ferenc Cross, myself, and the chemist. Medicine, these were the two persons behind the COVID vaccine, the what is called RMA. And you might receive the medal from the King of Sweden. And a few hours later is a huge banquet with 1,300 persons. It's extremely formal. And maybe here you need to be a woman. You might be seated close to the King of Sweden. Maybe it's not so spectacular being in England because you have lots of royal family, but for me, as French person, it was a bit special. So with that, I would like to thank you very much. This is a picture of the present group working in Sweden with many very good senior scientists in this group. You need always some organization financing the research. And I would like especially to thank John, Amel for a very nice, I would say collaboration and interaction during almost 40 years. So thank you very much. And
Thank you, Anne. I've got to get my notes out. I don't want to fluff it in front of a Nobel Prize winner. So thank you very much for a fantastic talk. I think it was a beautiful introduction to the field with lots of juicy morsels and technical detail for the specialists, so that was really appreciated. It's been a great privilege and a lot of fun to work in this field that you pioneered. I think the roller coaster is a good analogy. Although I was thinking in Sweden, don't you mostly have open prisons? But I might be wrong about that. I know that sentiment of feeling privileged and rewarded by working in this field is shared by many people in this audience. So postdocs, PhD students, other members of faculty, not only from Imperial, but from, as you mentioned, across London. We've got many of them here, as well as further afield. So, for example, at the CLF, there is a facility providing harmonic pulses, which wouldn't exist if it wasn't for your 40 picosecond YAG laser. And so, we're all extremely grateful and privileged that we've had the chance to follow in your footsteps in the exploration of high harmonic generation Attosecond physics. At Imperial, for which I can speak, obviously, we're having been here during this period and worked with colleagues in this fascinating area. We've been really lucky, as John pointed out, to build a community in this area. And even though we still haven't exactly agreed on how we should define the cutoff, which is an open question that perhaps we can ask you about. So I'd like to round out by thanking you again for a great talk, for your inspiration and leadership in the field, which continues, as we've seen with these recent works. You guys just never stop. You're always producing great results. So I'd like everybody to join with me to thank you for also your visit today and the time you've spent talking to the students. They were very grateful for that, to have a chance to chat with you. So let's thank Anne again.
thank you.
And here is some college merch for you.
Okay, I need to take this one. Yes.
And I realised actually it's a perfect match for her jacket.
Yeah.
So,
With my hair.
you know, maybe one of your kids can have that. I'm not sure whether that's exactly what you would wear. I mean, perhaps if you met the King of Sweden
yes,
again,
I
you
play
could.
tennis. I need caps. Yeah.
Good. And the other thing is that Anne has kindly agreed to take some questions.
Yes.
I asked her if there were any particular things. She said they can ask me about anything.
Yeah.
Obviously within reason. And she did mention, for example, being a female physicist, winning the Nobel Prize, or it could be physics. So there's time, I think, for some questions. So please, if not, I'll start off with one. But Is there anybody? Okay, there's a question at the back. Do we need the microphone to go back, or?
So my question is, how complex is that, the complexity of ionization electrons, especially given the nature of the inert gas and the stability of the S state? How difficult is that?
I think I didn't get the question.
Yeah, you give energy and you ionize the electrons from the S state, and you're using inert gas and helium, and both are like very stable, and the stability of the S state itself is very strong. So how?
Yeah, no. This is a weak. The last part of this talk, it was not a strong field at all. It's a weak field. So this I maybe should have said a little bit better. In all of this, this is the beauty of the Rabi technique. The red photon here. This is weak. It's less than 10 to 12 watts per square centimeter. So we can use perturbation theory to understand what is happening. This is weak field. And we make sure we don't multiphoton ionize with the laser when we do this type of measurements. Yeah.
Thank you, John. Well, it's a beautiful story with argon 3s and the shake-up effect, and the effect on the coherence of the outgoing electron wave packet. I just would like to make a short comment that the other half of that story is the coherence which can be imparted on the remaining ion, where you have coherent population of a series of shake-up states. And as a result, which are very long-lived, and as a result, this breathing ion expands and contracts and expands and contracts again and again. And that's just the other half of what you're doing, even if you're not measuring that.
Yeah, I mean, of course, it would be very interesting to measure the ion, but it's require a little bit different experimental techniques. We haven't done that yet. But
thank you.
Yes.
I might just comment, of course, this is exactly what you can do with the free electron laser methods, because they give you this localization because of the edge, the atomic edges. And so that's why we can use those X-ray pulses, pump probe schemes, to really look at charge migration directly. So look at the hole left behind by the electron.
Yeah.
Thank you very much for the talk. It was very interesting, even as someone not in the field. I'm curious about your discussion about the phase match in the high harmonic generation. How it has to be like, the intensity has to be high enough, but not too high. Was it just by chance that you had hit upon like the right intensity when you first were doing it, or was it a matter of you had calculated, oh, we need to be within this intensity bandwidth? Or was it just, we have this intensity, we'll go with it, and then when you went to higher intensities, you found it didn't work as well? Or, I'm kind of curious as to whether that was a happy accident or intentional.
This is a very good question. When we did the experiment 87, this was pure luck. This is what I mean. You need to have a little luck in your career, I guess, to get the Nobel Prize. And this is, to be honest, I can answer a little bit differently. Especially since after I got the Nobel Prize and I started to tell this story, I was wondering how could we see these harmonics with 40 picosecond laser pulse? And I was telling sorry, and then it was really, what happened? Why? Because 40 picosecond is really long. Now we're using 20 femtosecond, maybe 100 femtosecond, but this is 40 picosecond. And recently I got the answer. You want to know why? And it's really phase matching. Can I draw here? Yes, I can. Yeah. Yeah, it's enough with one. I can And this is about phase matching in this transient phase matching regime, where you need a certain ionization degree to get phase match. So if you, I'm plotting here the intensity of one harmonic, doesn't matter which one. So this is the intensity. This is your signal as a function of intensity. Okay? And if you work with 30 femtosecond pulse, you get something like this. I don't care what is. Now, what happens if you use... yeah, okay. Now, so this is with 30 femtosecond pulse. Now, what happened with 40 picosecond pulses? Actually, you reach this degree of ionization much earlier because it's a long pulse. So actually, the corresponding plot is here. So much lower intensity. We are 10 to the 13 watts. So in other words, depending on what you want, but there is an optimum pulse duration depending on the intensity. If you have very high intensity, you need to have a short pulse. But if you have a low intensity, then you reach phase matching much earlier, and then it's. So I think we were here. Really luck under conditions, really pure luck. Yes. But it's also amazed me, I still understand things about this now, which shows that this phenomena is extremely rich, and I'm sure there are still many things to learn.
Hi, Alan. Well, thank you so much for your lecture, and it was a pleasure meeting you before. As someone who's in the field, I want to ask, what do you think? I know you showed a brief summary of the prospects for the future, but right now, what do you think the focus should be? And do you think, especially when studying electron dynamics, do you think the focus should be on the probe shortening, or are they the setups we have at the minute with the X-fills and the HHG tabletops, are they already ready to be used? And should we focus on the pump instead? And if so, are there any techniques that you find especially interesting?
Yeah, I just can put that again. And even that. I think the field is very, very open. And I would say some of you are very young. Yeah, be creative. So it could be manipulating the probe, it could be manipulating the fundamental, or both. But I think there are many. This process is so rich, and there are so many applications. Now, if you look at application, I would like to say it like that. I think this part is very important for the field, that really show to the outside world that this technique can really be used to understand complex processes, so that we can really solve some issues. So I would put a priority here. Now, of course, it's also there are industrial applications, metrology technique, imaging technique. This is also very important, and this is kind of fun. This is what I showed in the end. It's no idea whether it leads anywhere, but it's kind of interesting. So very open. Yes, many things to do.
Yeah, thanks again for the great talk. I wondered if you'd noticed any significant changes day to day since winning the Nobel Prize, like more emails, more news reporters, anything like that?
Yes, many. I would say it's like getting a new job called outreach, giving many lectures, and I'm prioritizing a little bit giving lectures to universities and schools. Actually, this is a lot of fun to talk about that at schools. They like the electron in a prison very much. Yes, many, but I feel it's a little bit now I got this honor, I feel it's a little bit my responsibility also as a woman to not to stay in London in my my house, but really to go a little bit around and to talk about attosecond science.
I wanted to ask, are you using machine learning in any part of this work?
I guess I'm a little bit too old for that myself, but for example, here it's a little bit of, it is a little bit of some kind of machine technique, this transition from here to here. But I would say not very much yet, but more and more. That's the answer. And it's not myself, it's my younger colleagues.
So I think we've run out of questions. One thing in relation to the question that was asked about the perks or the changes that the Nobel Prize brought, it made me laugh when you mentioned over coffee this morning that her institute gave her a free parking space for her bicycle.
Yes.
As the reward. You hear that Stanford has its Nobel Prize parking bay, right? So
and the motivation was that Lund was an ecology town.
Yeah,
So
but I think it also sums you up as probably the nicest and most modest Nobel laureate that I think any of us are ever going to meet. So on that note, let's thank Anne again, and yeah, thank you very much.